Hello, Georgi Romanic here. Today we are going to look into somewhat tricky integral. It's integral that kind of looks like Gaussian integral, but it's not Gaussian integral. You will remember that Gaussian integral was integral from negative infinity to positive infinity, e to negative x squared dx. And the solution was square root of pi, my previous video. But today we will ask ourselves what happens if we multiply that exponential Gaussian function with x squared itself. So integral is between negative infinity and positive infinity, x squared e to negative x squared dx. This integral is more difficult, of course, to solve than Gaussian integral, and to solve it we will use integration by parts, and then we will also use our knowledge of Gaussian integral. Let's do it. Integral that we wish to solve is integral from negative infinity to infinity x squared e to negative ax squared dx, where a is a constant. Before we do anything with this integral, kindly recall from my previous video that the integral in the form negative infinity to positive infinity e to negative ax squared dx is the so-called Gaussian integral, and we analytically solved it to have solution that is square root pi over a. Now you will right away see that this integral is exactly the same as this one except for this x squared, which makes it more tricky. So let us call this integral I, and how do we solve it? Well, there are many videos I noticed on YouTube that solve this integral using the so-called Feynman's method. And trust me, nobody is bigger fan of Richard Feynman than me, but here I will use traditional method of integration by parts. And that's because that method is traditionally used in high school or undergraduate mathematics courses, so you can relate to that method and then you know how to solve this integral using that standard method. Integration by parts says that integral of functions f dg can be written as fg minus integral of functions g df. In our integral I will say that my function f is equal x, and my function dg is x e to negative ax squared dx. As you can see, I picked up just one x from this x squared and called it f, and the rest was dg. At any rate, we see that we need df. Well, df from here is very simple. df is dx. But we also need g, which means we need to integrate this, and g would be equal integral x e to negative ax squared dx. Which means we now need to solve this integral over here. But that integral is also relatively simple because I solved it in my previous video when we were dealing with Gaussian integral. You can solve it by introducing a substitution, but I told you that more fancy way to do it is to identify that x dx can be written as 1 over 2 dx squared. And then I have here e to negative ax squared. And now this is table integral because this is dx squared and here I have x squared too. It would be like e to x dx. And of course solution of this is negative 1 over 2, these two, I lower a down, and then this is negative a to negative ax squared. So now we have our f function, df function, dg function, and our g function, which means we can go back to our formula for integration by parts and write that our integral I is equal f, and f is x. G, and g is negative 1 over 2a e to negative ax squared minus integral g, well, that's again this negative 1 over 2a e to negative ax squared times df. df is dx. Now we can a little bit manipulate this to be in a nicer form. This is in the limits between, I forgot limits, negative infinity to infinity, and this integral is negative infinity to infinity. So this over here is negative x over 2a e to ax squared. You see, because this is negative, I lowered it down, now it's positive. In the limits, negative infinity to positive infinity. Minus and minus will give me plus integral from negative infinity to positive infinity. And this 2a I can bring in front of the integral, and I get integral a to negative ax squared dx. When you look at this integral, you have a sense of happiness because you identify it's this integral over here. It's Gaussian integral. So the solution of this integral is 1 over 2a, which is this constant, times square root pi over a. The only thing is to evaluate this limit over here, and let us do it. So if we have limit, let's first evaluate limit when x goes to positive infinity, upper limit, of x divided by e to ax squared. Of course, I don't care about these constants, 2a, negative, who cares? This is equal, when x tends to infinity, numerator is infinity, and e to infinity is also infinity. And whenever you see limit infinity over infinity, you get that beautiful feeling of L'Hopital's rule. And L'Hopital's rule says, in these cases, proceed with taking derivative of numerator and derivative of denominator, and then evaluate that limit. In other words, we will evaluate limit x tends to infinity. Derivative of x with respect to x is 1. Derivative of this exponential function is 2ax e to ax squared, and this is equal 1 divided, when x tends to infinity, denominator is infinity, and 1 to infinity tends to 0. And you can convince yourself you get the same result if you try to solve this limit when x goes to negative infinity, which means this term over here simply collapses to 0. And our integral I that was that was equal to integral from negative infinity to positive infinity, x squared e to negative ax squared dx is equal simply this 1 over 2a square root pi over a. Of course, you can be a little bit more fancy and say that this is further equal if you manipulate this square root of pi, and then you combine 2a and square root of a to get 2a to the power 3 over 2. And this is solution of our integral that looks like Gaussian integral, but not quite. But this integral is quite often encountered in natural sciences, and it's important to know it. Now we are equipped with knowledge on Gaussian integral, as well as this integral that kind of looks like Gaussian, but it's not really Gaussian integral. And this is all that we need now to go back to our video on Boltzmann distribution and determine the value of that pesky Lagrange multiplier. You will remember we derived the entire distribution, but there was that unknown parameter that needed to be determined. That parameter, I will tell you right now, is equal 1 divided by kT, where k is Boltzmann constant 1.38 times 10 to power negative 23 joules per Kelvin, and T is absolute temperature. On many channels, they would tell you it can be demonstrated that Lagrange multiplier is equal to that. We don't tell you here anything without demonstrating it. And in the next video, you will see the demonstration of that concept. Until then, goodbye.